Recording. Okay. So we're being recorded, I believe. Are you seeing a symbol saying the?
Yes.
Yeah. So I'm writing down the web page for the course. I think this is what I called it. If not, you can just search my homepage and you find the web page for the course. So this web page contains the homework exercise and some references. So I'm following approximately 4 or 5 books, but I'm not following one particular book. And these books are all on the homepage. Now, that's about grading and about the homepage. I'm not using Moodle hardly at all. So people who want to join the course, send me an email and I'll send you the link to the lectures. All of you are here obviously have the link to the Zoom and you can share it with anybody that you'd like to share it with. And I don't think I'll be using the Moodle other than that. So we just need the Zoom lectures and I'll send people who are interested in the recordings, send me an email and I'll send you email notifications about the recordings. About our, this is my first time giving a Zoom course. About our behavior on Zoom, I appreciate any interruption because I'm not used to this and I cannot see you and I don't know whether you're understanding. Please stop me whenever whenever you feel like it, so we get a little bit of interaction here, and ask questions. I don't really care whether you have your camera on or off, but if you are asking questions, please turn your camera on so I can see you and so that everybody else can see you. I think that's all I wanted to say in terms of introduction and generality.
Can I ask a question?
Sure.
Will you also share the notability notebook of the course?
I can share it.
Material?
I don't. Yeah, I can send it. I guess I can. If people want it, I can send it to them individually by email. I don't expect it to be. Knowing myself, I don't expect it to be extremely well organized. But if people want to look at it, I'm happy to send them a copy. Okay. Let's get started. So the course is about, so the word geometry, the course is called Geometry of Numbers, but as you may have noticed, I'm calling it, so you're seeing my cursor, oh, you're not seeing my cursor because okay, so this is what I call it a course on lattices. Lattices and geometry of numbers are basically the same thing in mathematics. And the name geometry of numbers is the name given to this field by Minkowski, who founded this topic. So the topic was founded by Hermann Minkowski. Roughly in 1880 until 1909 when he died. And in 1910, a year after his death, Minkowski's book called Geometrie der Zahlen, Geometry of Numbers, was published. So this is a year after his death. And this is the name that he used. And this is the name that became commonly used. And this field has very interesting connections with lots of other fields in mathematics. The two fields of mathematics that were envisioned by Minkowski are convexity theory, which is also another field that Minkowski made a lot of contributions to. So geometry of convex sets in Euclidean spaces, and number theory. And originally, Minkowski got interested in geometry of numbers because of questions in number theory. And that's why it sort of became a sub-branch of number theory called the geometry of numbers. There's an additional field so let me write it down. So it's connected to the following fields in mathematics: convexity number theory, particularly the investigation of number fields. Diophantine approximation, which is another branch in number theory. Diophantine approximation is the branch in number theory in which you have real objects like real numbers, real vectors, real matrices, and you're trying to find good approximations to them by rational numbers or rational objects. Homogeneous dynamics, which is something we'll spend quite a bit of time on in this course, and also recently computer science and electrical engineering. So during the course, I will tell you about these relationships as we go. They're not the main focus of the course. I thought I might start off by saying a little bit of why the computer scientists are so interested in it, but I think I'll postpone that. So computer scientists and electrical engineers are probably the most active community now studying the geometry of numbers, with a lot of breakthroughs that are really purely mathematical. And we'll get to some of those during the course. And so let's just start. So today will be sort of definitions and basic algebraic data. So the geometry of numbers or lattices, there's the algebra behind it, which is not terribly complicated. It's not trivial, but it's not terribly complicated. And then there's a lot of geometry and dynamics. So we're just going to start off today with the definitions and the algebra. So definition, a lattice in Rn is a subset in which there is a independent set of vectors, of n vectors. So this is a basis, a real basis for Rn. In the language of linear algebra, you obviously just say basis, but I'm going to be distinguishing over things that happen over the reals to things that happen over the integers, such that L is the integer linear combination of the vectors in this set. So it's the span, but the span over Z of these vectors. So this is just a notation of what I mean by the span over Z. Okay, another notation that's often used is this notation. So I'm taking n linearly independent vectors and I'm looking at all their integer linear combinations. Let's do some examples. Let's start with n equals 2 and v1 e1, v2 e2. The first two vectors of the standard basis. And so then, oh, I'm sorry, I should have added here. Okay, let's be fancy with this. Let's see if I can make this work. No. So I'm still getting used to all this technology. Make a little room here. The collection V1 up to Vn is called a basis for L. Okay. If L is generated over Z by the vectors Vi, then I call the Vi's the basis. And so what's the lattice generated by these two matrices? This is the integer lattice, so this is V2. Is the span of these two, span over Z of these two vectors. And more generally, Zn, the span of the n standard basis vectors, is called the integer lattice. Okay, and despite the fact that this is the first example that everybody gives, algebraically it's the only example, but geometrically it's not at all a typical example, as we're going to see during the course. So this, I'm not explaining yet what I mean by the geometry of the lattice, but the geometry of the integer lattice, as you'll find out, is very, very different from the geometry of a typical lattice or a general lattice. Okay, let's do another example. Let's stay in, let's stay in 2 dimensions, and let's replace V2 by E1 plus E2. So 1 comma 1. So then we get the same. So I'm claiming that we get the same lattice if we take these 2 new vectors and generate over Z. And so this is another basis of Z2. So bases are obviously not unique. And why is this? Well, let's let L be this set. And so since V1 and V2 are in Z2, L is contained in Z2, but E1 equals V1, E2 is V2 minus V1. If you look at this, these 2 definitions, and so E2 itself is an integer linear combination of elements of L. So E1 and E2 are both in L, and therefore their span over Z is also in L, but this is Z2. So we get the 2 inclusions, and so Z2 is equal to L. So we've expressed the same lattice in 2 different ways by choosing 2 different bases for the same lattice. Let's give an example of a lattice that's not, so this is example 3, that's not Z2. So let's take V1 to be E1 again in dimension 2, but let's let V2 be cosine pi over 3 sine pi over 3. Okay, so these are 2 vectors of length 1 in R2. And if we draw a picture, this is the origin. This is 1, so this vector here is E1. And if we make an equilateral triangle, sorry, this is what I'm calling V1, I guess. And this is V2, the other edge of an equilateral triangle. And if you look at all the points that can be obtained by integer linear combinations of these vectors, you'll see this pattern. You're tiling the plane with equilateral. These are vertices of a tiling of the plane by equilateral triangles. And this lattice has many names. So this is sometimes called the honeycomb lattice, or the hexagon lattice. And it has many other names. And it's an interesting lattice for many reasons, as we'll see. Let's do a much more general example. So this is example 4. Let's let A be an n by n matrix invertible. So A is in GLNR, which is the matrices n by n matrices of non-zero determinant. What's going on? Yes. My okay. And let's look at L, the image of Zn under the linear transformation corresponding to A. So we're taking the integer lattice and we're pushing it by this matrix. And let's try to see what this comes out to be algebraically. So this is A applied to sums. These are the elements in the integer lattice, and you apply A to all of them. But this is A is a linear transformation, so I can push it inside. And so it looks like this. And if you think about what this means, this is the span over Z of AE1 up to AEN, which is the span over Z of the columns of A. Okay? Please stop me if there are any questions. I see that there's a question on chat or something going on chat. Oh, thank you for the, there's a link to the homepage. Thank you. To the course homepage. So this is what you get when you apply a linear transformation to the integer lattice. You get the lattice spanned by the columns of the linear transformation. And this computation shows a proposition. So corollary of the computation, any lattice is of this form. Any lattice can be obtained from the integer lattice by applying an invertible matrix, because if L is the span over Z of V1 up to Vn, you define A. So this is a notation I'll be using. A is the matrix whose columns are the VIs. So since the VIs were a basis, they were linearly independent, A has non-zero determinant. And by the previous discussion, L is the image of Zn under A. Let's ask, so we're seeing that the group GLNR is a group. If you're seeing that the group GLNR acts transitively on all lattices in Rn. It's pushing Zn to every other possible lattice. And let's ask question. We saw in the first two examples that the same lattice can have two different bases. Let's ask how many possible bases there are. Let's solve this with first for the integer lattice Dn and see what we come up with. So proposition, let's let G, L, and Z, that's our notation for matrices over Z whose determinant is plus or minus 1. So before I continue, take a close look at this notation because it's somewhat confusing. the definition of GLNR is all matrices, n by n matrices with determinant non-zero. Here I'm taking integer matrices. That's why I put this Z inside the brackets. So I'm taking integer matrices, but I'm not allowing non-zero determinant unless it's plus minus one. So that's not a completely obvious notation. I'm just pointing that out to you. But this is the standard notation for this. And so what do I want from this proposition? Then one, GLNZ is a group. Is a group and consists of all integer matrices which are invertible and whose inverse is also an integer matrix. And once we know that this is a group, I want to claim that this is exactly the set of matrices that preserve GLNZ. And you'll see in a moment that with this group in hand, we can figure out exactly how many different bases Zn has. So let's prove this. Let's prove this proposition. So if you look at the definition of GLNZ, it's clearly closed under multiple. First of all, GLNR, if I put an R here, the invertible matrices, that's clearly a group under matrix multiplication, right? Because matrix multiplication satisfies the group axioms, and the existence of an inverse follows from the fact that the determinant is not zero. And I'm claiming that this is a subgroup. So clearly it's closed under multiplication, because if you multiply two matrices whose determinant is plus minus one, you get a matrix whose determinant is plus minus one. If you multiply two integer matrices, you get an integer matrix. And what about invertibility? So I'll just write that down. So clearly GLNZ is closed under multiplication, matrix multiplication. That's a group law. And if you have a matrix here, then there's a Cramer's rule for inverting a matrix. And it tells you that the inverse matrix is given by 1 over the determinant times the so-called adjugate matrix. So the determinant is plus minus 1 here. The adjugate matrix is the matrix that you get by taking minors of size n minus 1 by n minus 1 and taking their determinant. So this matrix is clearly an integer matrix because we're taking determinants of integer matrices. And so this is an integral matrix, and then we're dividing those integers by plus minus 1. We're staying inside integers. And so this is also integral. And of course, it also has determinant plus minus 1 because, again, the determinant is multiplicative. Okay, so this proves that GLNZ is a subgroup of GLNR. And so every element in GLNZ satisfies these properties. Satisfies these properties. It's integral, it's invertible, and the inverse is an integer matrix. And conversely, if we have such a matrix, if A is in MNZ and A inverse is also in MNZ, then the determinant of A times the determinant of A inverse is the determinant of the identity, which is 1, but this is an integer, and this is an integer because they're both integral matrices. And so when you multiply two integers and get one, you get that you have to have it, these integers have to be plus minus 1. So I've proved that, I've proved the first assertion of this proposition. Okay, let's talk about the second assertion. So I'm claiming that the stabilizer of Zn under matrix multiplication is exactly n by n integer matrix. Integer matrix is the determinant plus or minus 1. So this is part 2. And let's start with this direction. So I take an invertible matrix in GLNZ and I apply it to Zn. And let's look at, I want to prove to you that A of Zn is Zn. So what is A of Zn? A of Zn is the span over Z of the columns of A. The columns of A are integers. And so this has to be a subset of Zn, because it's spanned over Z by integer matrices. And on the other hand, so applying the same, by the same logic, A inverse applied to Zn is also a subgroup of Zn, or contained in Zn. And so now we apply A to both sides, and you get that Zn is contained in AZn. Okay, so in total, I've proved to you that AZn equals Zn. So matrices in GLNZ do stabilize Zn, and that proves, maybe I'll put a circle around it, that proves this direction in the if and only if. For the second direction, let's assume A of Zn equals Zn. So this means that, in particular, the columns of A are in Zn, right? Because the columns of A, Zn are elements of the lattice, and we know that this lattice is Zn, so that means that A is an integer matrix. And then applying, again, A inverse to both sides, we get that A inverse, so Zn, what I mean is both sides, I apply A inverse to both sides of this formula, and I get that A inverse Zn is equal to the A inverse of Zn. And this implies, by the same logic, that A inverse is in Z. And so by part 1, this means that A is in GLNZ. Okay, so this proves the proposition. Now that we have the proposition, we can discuss the question that I asked before. So this is corollary 1. All the bases of Zn. Well, let's already do a general. Yeah, let's do a general case. So, just a moment. Yeah, all the bases of a lattice, of any lattice, Okay, so what I'm telling you now is that you can get from any one basis to any other basis of a given lattice. Sorry, the given lattice, this lattice, I can move from any one basis to any other basis by applying a matrix in GLNZ. Okay, in particular for Zn, you can take the standard lattice, GLNZ. So let's write the special case. In particular, for Zn, which is the span of U1 to U1, U1 up to UN is a basis, if and only if the matrix belongs to GLNZ. So the different bases of Zn are exactly the columns of matrices in GLNZ. In other words, in another language, GLNZ is acting simply transitively on bases of Zn. Let's prove the corollary. So we have two bases for the same. We have two bases for the same lattice, V1 up to Vn, U1 up to Un, and this is equivalent to saying that B applied to Zn is A applied to Zn, where B is formed by putting the VI's as columns of a matrix, and A is formed by putting the UI's as columns of a matrix. Right? That's what we saw earlier. This lattice is exactly this lattice if we make this the definition of B. Okay, so if we define A and B in this way, we have equality between BZN and AZN. And now we can left multiply by B inverse. So this happens if and only if B inverse A Zn equals Zn for the same choices of B and A, which means by the previous proposition, so you're seeing now that B inverse A fixes Zn. So by the previous proposition, B inverse A equals gamma for some gamma in GLN. Okay. So that means that A equals B gamma for some gamma in GLNZ. What does it mean by gamma? The gamma appears on the right. What it's performing is linear combinations with coefficients in gamma of the columns of B. And so let's go back to this formula. What this is saying is that the UJs are linear combinations of the VI's with coefficients in this matrix gamma, which exactly means the UJs are the columns of A, the VI's are the columns of B. That exactly means that A is obtained from B by right multiplying by a matrix in gamma. Okay, again, because right multiplication, so I'll leave that to think about maybe. So this is exactly equivalent to star, and here I'll put a remark, note that right multiplying B by gamma results in linear combinations with coefficients in gamma of the columns of B. Okay, so that's proving the proposition. I'll take a pause for I see something in the chat. So let's take a look at the chat. Oh, so there's
sorry, my bad. It was some problem with my computer.
okay.
All good. Thank you.
Like I said, just stop me if you have questions. I'm much happier stopping every so often because I have no idea whether I'm going too fast for you or not. And so stop me with questions. Let's do a very important corollary of this discussion. So this is corollary 2. And I want to talk about the collection of all lattices. So there's a bijection. And this will be an important bijection in everything that follows. We take all lattices in Rn, and this is in bijection with GL and R over GL and Z, where this notation, this quotient space, so maybe I'll write it on a separate line. So this, when you have two groups, G and gamma, G mod gamma with gamma written on the right is the collection of right cosets of this form. So this is the coset space. And it's going to be important in several computations that follow to distinguish the right coset space from the left coset space. So I'll just introduce a notation that I'm not using right now, but I'll just have it in mind, so you have it in front of you. Whenever I want to talk about cosets, left cosets, in other words, where gamma appears on the other side, I will use this notation. So most of you probably are already familiar with this notation, but recall that if G is abelian, there's no difference between these two collections, but if G is not abelian, it's a different class of cosets. Okay, it's a different way of partitioning G into pieces. So in this proposition, I'm claiming that the cosets, when you divide, these are both groups, and when you make this coset space, you're in bijection with a collection of all lattices. Okay, now when you first see this corollary, you might think this is kind of a bit of a trivial or silly corollary. Why? Well, all I'm saying right now is it's a bijection. So if two sets are in bijection, that means they have the same cardinality. And it's trivial to figure out that the cardinality of both of these sets is the cardinality of the continuum. Okay, so that's a very easy thing to figure out. But of course, we're going to be interested exactly in what this bijection does for us in many, many situations. And in particular, we're going to use this bijection to put a topology on this space, to put measures on this space, and so on and so forth. So it's going to be an important. So it's not just a bijection, it's kind of an interesting and important bijection. Why is this true? This is a corollary to proof. It just follows from a general fact. In group theory, which most of you, I'm sure, know already, but I'll just repeat it because it's important. So let G act on a space. I'm recalling what this means. The space is called X. So this means, i.e., we have a map from the product G cross X to X. This is the Cartesian product. And the notation for this is just a notation. So the map takes a pair G comma X to an element which I just denote by Gx. And it has to satisfy two axioms. The identity doesn't do anything. And the composition rule is some kind of something you might call associativity, or this is the group action law, I guess it's usually called. Okay, so this is what I mean by an action of a group on a space. And so if you look at this formula, if you've forgotten what this is important. So in this formula, you're multiplying in the group first, and then you're applying the action to x, so you end up with an element of x. Here you take x, apply g to it, you have a new element of x, then you apply g1 to what you got, and you have a new element of x, and these should be the same. So this is a group action on a space, and suppose the action is transitive, which means that you can go from any point to any other point. Then the map G of, then for each, I'm sorry, we're gonna, for each fixed x0 in x, the map G0 to x given by G0 maps to Gx0, where G0 is the stabilizer group of x0. This map is a bijection. Okay, so this is a very basic fact in definitions of group actions. And if you don't remember why this is true, just recall it. It's just a little calculation, but it's quite important for us. And we've already proved that in our setup, to use this in our setup with x0 being equal to the integer lattice, G being equal to GLNR, and G0 being equal to GLNZ. We proved exactly that the action of GLNR on lattices is transitive, and we proved that the stabilizer of Zn is GLNZ. Okay, so that's the second corollary of this. Here's another important corollary. If you have a lattice L, which is the image of Zn by matrix A is in GLNR, then the absolute value of the determined array depends only on L and not on A. And why is that?
Is A in GLNR or in MNR?
A is in GLNR.
So like the sign, its sign is.
Sorry.
It's like the determinant of a matrix in GLNR is only plus or minus 1.
No. The determinant of a matrix in G. That's what I said that when I warned you.
Oh, GLNR. I'm sorry. Yeah.
I warned you that the notation is confusing. GLNR determinants are allowed to be any number except 0. And now I'm taking the determinant and I'm taking the absolute value. Okay.
Thank you. I
And
got
so
confused.
this is a positive. This is a positive number, but it's not necessarily 1. And so proof. If you had two matrices, if A1Zn equals L equals A2Zn, then we saw before there exists gamma in GLNZ such that A1 gamma equals A2. This is what we just proved. This is this bijection that we're discussing. And so the determinant of A1 is plus minus the determinant of A2 because the determinant of gamma is plus minus 1. So their absolute value is the same. So that's the proof of the corollary. And so this number, so we found an important invariant associated with lattices, and this is called the co-volume of L. So this number, absolute value of determinant A, so this is a definition. Absolute value of determinant A is called the co-volume of L. And the notation that I'll use is, this is notation, it's for volume of L. So in the literature, you'll see notations like D of L. Sometimes people will write the determinant of L, which is confusing because it's actually the absolute value of the determinant. And there are many other possible notations. And actually, sometimes you'll see a strange square in the, or a square root of some determinant. So, okay, I'm just warning you that if you open the books, there's something that's slightly confusing about the notations that people use for this object. We'll say more about that later. And so this is the co-volume. And I think this is a good time to take a break. Yeah, so let's take a 10-minute, so 12-minute break to make the numbers match up. So let's meet again at 10 past 11, unless people have questions. Maybe this is a good time for some questions if anybody has questions. Okay, so if no questions, we take a 12-minute break.
ברק, אפשר שאלה מנהלתית קטנה רק?
כן, כן, בטח.
אתה תעלה את ההקלטות, אני לחוץ על ההקלטות, סליחה, זה פשוט לא יהיה בשעה האחרונה כל שבוע, אז אתה תעלה את ההקלטות.
אני עוד, מה שהבנתי זה שיש עכשיו איזשהו שינוי במדיניות הקלטות של האוניברסיטה, ובדיפולט הם פעם היו מגיעות אליי למייל, ויכולתי לעשות איתם share בקלות, ואמרו שזה כבר לא יהיה ככה. התוכנית שלי זה לעשות להם share לכל מי שמבקש פשוט לשלוח את הלינקים במייל, אבל הבנתי שזה אולי קצת יסתבך במהלך הסמסטר, והם יעברו למערכת הפנופטו הזאת שאני לא יודע לעבוד איתה עדיין. אז השורה התחתונה היא, תשלח לי מייל ותבקש ממני את ההקלטות, ואני אשלח לך לינק, ואם אני רואה שזה יסתבך, אז אני אעשה איזשהו קישור. אני לא אוהב לעבוד עם המודל, כי אני לא כל כך מכיר אותו, אז אולי אני אעשה קישור מההום פייג' של לדעתי גם לפי החוקים של האוניברסיטה, הם לא רוצים שאני אעמיד את ההקלטות האלה, אני חושב, באתר שלי לכל העולם לראות, אני לא משוכנע עדיין. אז אני עדיין לא הבנתי עד הסוף מה אני עושה, אבל כרגע התוכנית שלי זה שכל מי שולח לי מייל ומבקש את ההקלטות, אני שולח לו את הלינקים להקלטות. יכול להיות שזה...
תודה.
בבקשה.
כרגע אתה מנסה לדבר, אתה על מיוט.
אני מדבר טיפה לעצמי, אני קראתי את ההודעה בצ'אט של להגדיל את הלוח. אני מנחש שיש, אולי אם אני אסובב את זה פשוט, אז... אני לא יודע לעשות את זה. אולי מישהו פה יודע. סליחה, אני לא שומע אותך טוב. אתה לא נשמע טוב. אתה לא נשמע טוב. תגיד עוד פעם?
טוב, אז אני אכתוב.
כן, אוקיי. בסדר, אז בוא אותי שומעים. אם מישהו יודע, אני משתמש בנוטביליטי על אייפד, אם מישהו יודע איך אני שומר על הגודל אצלי כדי שאני אוכל לכתוב בקלות, אבל מקטין לכולם את הפונט ומגדיל כביכול את היריעה שנראית על המסך, אז אני אשמח לשמוע, כי אני לא יודע לעשות את זה, וזה באמת יכול לעזור. ואם לא, אני אחפש את זה אחרי השיעור באיזשהו סרטון הדרכה או משהו.
ברק, אתה יכול לגלגל למעלה לחלק של הביאקציה עד סוף ההפסקה?
כן. מה השאלה אבל יותר ספציפית? מה לא ברור?
לא, אני פשוט לא... אני רציתי להעתיק את זה ולא סיימתי להעתיק.
פשוט להראות את זה?
כן.
אז אני... אוקיי. זה הניסוח. ואני לא יודע איפה אתה רוצה לראות שוב.
את ההוכחה.
ואז אני אמרתי מין טענה מאוד מאוד כללית על חבורה שפועלת על מרחב. אם היא קיימת תכונות מסוימות, אז בדיוק יש את העתקה חד-חד-ערכית בעל מהסוג שאמרתי, ואת התנאים של הטענה המאוד מאוד כללית אנחנו בדקנו בעצם. אז לגלול עוד קצת או שאתה יכול לראות את זה? עכשיו אני אקטין רק לצורך זה.
כן, זה מצוין, תודה.
אם כבר מבקשים לגלול גם צריך למעלה, בניסוח של המסקנה הראשונה.
כן, אז בזמן שמישהו מסתכל, אני אקרא בפיד הרשימות מה זה מסקנה הראשונה. מה השאלה?
תוכל אחרי זה לגלול למסקנה אחת, בניסוח שלה?
כן, אז מי שביקש קודם את הטענה שעכשיו על הלוח שיגיד לי שהוא סיים, ואז אני אגלול למעלה.
אוקיי.
בסדר, סיימתי, תודה.
אז זה היה. לא. טוב. Okay, so let's continue. So now I want to define a fundamental domain for lattice. So this is a new topic. So here we're going to bring in just a tiny bit of something beyond algebra, which is a little bit of measure theory. So let's let L be a lattice in Rn. And what is a fundamental domain? So a set omega in Rn is called a fundamental domain for L. If it satisfies the following property: omega is a Borel set. This is what I meant by saying that it's a little bit of measure theory. So we want a Borel set in Rn, and we want it to intersect every coset uniquely. So what that means is that for every x in Rn, there are unique elements of L and L, and let's write it somewhat differently. There's a unique y and omega such that there is L and L with y equals x minus n. So this statement 2 is saying that every x, you can translate it by adding a vector from the lattice to get a point in y, and there's a unique such point y. If there's a unique such point y, then you can invert this formula and see that L itself with this property is also unique. So another way of saying this part is to say that there are a unique y and omega and a unique L and L with this property. Okay, those two things are sort of easily equivalent. So what do we get from 2? Let me say item 2 of the definition in 2 different ways. So you could say that if you take all elements of L and translate omega by adding L to it, you get all of Rn. This notation, square union, this means disjoint union. Okay, so when you take omega and start adding L to it, you cover all of Rn, but every point gets covered exactly once. Another way of thinking about this is omega is a collection of equivalence class representatives for the relation x1 is in relation with x2 if and only if x1 minus x2 is an L. Okay, so you can easily convince yourself that this definition here defines an equivalence relation, and this tells you that the set of y's form representatives of equivalence classes, and the uniqueness says exactly that this is exactly could be taken as a collection of equivalence class representatives for this relation. And finally, just by definition of what cosets mean, this is just by definition means that omega is a collection of coset representatives representatives for the quotient Rn divided by L. Okay, if you remember your algebra course, the meaning of this object, this is a set. This is just defined to be the coset representatives for this relation. And recall also from group theory, this will come up several times. If Rn is abelian, or more generally, if this group is normal in this group, then this quotient space acquires the additional structure of a group. Okay, so in general, this might not be a group. In our setup, since we're discussing abelian groups, this is a group. In the general case, if this were not an abelian situation, this notation is sort of confusing in the general case. In the general case, if this were not an abelian situation, instead of writing x1 minus x2, I could write x1 times x2 inverse, or I could write x2 inverse times x1. And these would be different equivalence relations, and they would correspond to different coset representatives. In one case, it would be the right cosets. In another case, this would be the left cosets. For now, we don't care about this because we're in the situation of an abelian group. But soon we're going to do these kinds of tricks for the coset space that we already saw, GLNR over GLNZ, where GLNR is not an abelian group. And then there's a difference between right cosets and left cosets. So I'm just warning you that there's a kind of a confusing thing in group theory that's going to come up with this space of cosets. Okay, all of these are restatements of 2. What about 1? 1 is just a kind of a mild restriction on omega. You don't want it to be too crazy. You don't want to use the axiom of choice, for example, to construct it or anything like that, because we're going to be applying Lebesgue theory of Lebesgue measure to this set omega. But I'm not requiring much. It's just a general Borel set that serves as a collection of coset representatives. So let's do some examples. Let's take L to be the integer lattice Vn, and let's take omega to be the unit cube with which is left closed. Every interval here is left closed and right open. Okay, and so obviously this is a Borel set. It's neither closed or open, but it's definitely a Borel set. And I'm claiming that it's a set of coset representatives. So why is that? So for every real number x, we can define the integer part of x in the usual way. So this is the minimal, it's the maximal, sorry. The maximal integer less than or equal to x. And the fractional part of x is this number. And so the fractional part of x is obviously in 0, 1. And for any real number, there's a unique way to write that real number as the sum of a integer and a number between 0 and 1, not including 1. And this is the unique way to do it. And therefore, if we, so given v equals, maybe not v, y, say, equals y on up to yn in Rn, let's let x, the vector x, be the integral parts, y1 up to yn. And this is in Zn, and y minus x will then consist of the fractional part of y1, fractional part of yn. This is an element of omega. And because of the one-dimensional fact that this is the unique way to write a real number as the sum of an integer and a number between 0 and 1, this is the unique way of finding, maybe this should have been called, I'm sorry, this should probably have been called L. I think this is what we called L before. Let me just check the definition. Yeah, y equals x minus L, and y is in omega. I'm sorry. So this should have been, I just want to match the I just want to match things with the definition, and I apologize that the coefficients of x are being called y1 up to yn, but this is satisfying the properties of the definition. Okay, so this is obviously a fundamental domain for Zn, and so now what we can do is we can push this fundamental domain around using a linear transformation. So this would be example 2. Using a linear transformation, we can push this fundamental domain around to get more fundamental domains. And so, more generally, if L is the image of Zn by some matrix A in GL and R, and then A applied to 0, 1, n is a fundamental domain, for L. And the reason is that if you look at the two properties in the definition, well, if omega were a Borel set, then A applied to omega is still a Borel set. And if you think about the second property, for every y, for every x, you want to find a y satisfying this property, you pull it back by A, you find a corresponding y for Z for in the cube, and then yeah, let me write that down because it's easy, but I'll write it down. So for property 2, given x in Rn, define x prime to be A inverse of x, and y prime in so this comes from the fact that so this element now is an element of Z2B, and this comes from the fact that x prime that the cube is a fundamental domain for Z to the n, and then x is a y prime y equals a y prime is x minus a L prime. Call this guy L. This lies in R, so L. And so we've this proves property 2 for this lattice and this fundamental domain. Of course, you can check that the uniqueness also follows from uniqueness for Z to the n. Okay, so in this particular case, this domain that we've discussed is a parallelepiped. It's the higher dimensional analog of a parallelogram. It's a polytope with pairs of parallel opposite sides, n pairs of parallel opposite affine subspaces, and its volume. So this is sometimes so A. Oops, I'm sorry. A equals omega equals this is a parallelepiped, and it's called the fundamental parallelepiped associated with the basis AE1 up to AEN. And let's figure out why. So it's basically, okay, let's figure out exactly why. So let's just write it out. So A of 0, 1 to the n is so the cube 0, 1 to the n is just all linear combinations of the standard basis with coefficients in 0, 1, closed on the left and open on the right. And so this means, again, by linearity, this is all linear combinations so this is, if this, let's do a two-dimensional picture. If this is AE1 and this is AE2, then the set of all these linear combinations is this particular parallelogram. And recall that these elements over here give us a basis for our lattice, and every basis arises in this way. And so for every basis, we can take such a parallelepiped, and that's going to be a fundamental domain. So that's one example, and that's a very basic example of a fundamental domain, but it's not the only example, and it's sometimes not the best example. And let's just make a connection between this and the end of the previous lecture. So recall from calculus that the volume of the image of this cube under A is the absolute value of the determinant of A. Right, this is when we discuss the so volume for me will be Lebesgue measure unless I say otherwise. So this is Lebesgue measure. There's going to be a few measures in this. There are going to be a few measures in this course. So Lebesgue measure on our end, I'll usually denote by volume. And so in the first course on Lebesgue measure, one of the things that's taught is this transformation rule for Lebesgue measure. If you apply a linear transformation to a set, then the volume of the respective image is the determinant of the matrix in absolute value times the volume of the set you started with, and the volume of the unit cube is 1 by definition of Lebesgue measure. So this is the co-volume of the lattice. So the co-volume of the lattice is the volume of the fundamental parallelepiped. Okay. I have some pictures. So let's look at some pictures of these fundamental parallelepipeds. They depend on the choice of the basis. Yeah, here are two pictures. So this is, by the way, one of the references that I write down in the course homepage is to a course given in lecture notes of a course given in Tel Aviv in 2006 or 7, I believe, by Oded Regev. Oded Regev is a very well-known computer scientist. If you're interested in, he's now in New York. If you're interested in computer science and applications of lattice to computer science, I definitely recommend his the lecture notes from his course. And this picture is from his homepage. So what we're seeing here is two different bases of the integer lattice E2. This is basis number 1, and this square is the fundamental parallelepiped. This is another basis, and this parallelogram is also a fundamental domain. How do we know that this is the basis? Well, what we have to check is that if you take the matrix formed by the columns of these as with these vectors as columns, so you have to check that the determinant of 1, 1, 2, 1 is plus or minus 1. Indeed, here it's minus 1, so that means that these columns generate the same lattice. So this is a different basis of the same lattice, and this is a different fundamental domain. This is a picture of, so I said that a fundamental domain has the property that its images under the lattice fill up the space exactly with no overlaps. And so, I don't know, so I'm going to sort of try to trace one of these cubes. So if you look at this particular cube here, this is space number 1, and that's space number 2. That cube is a fundamental parallelepiped for a certain lattice in 3-dimensional space. And you see that these fundamental parallelepipeds tile space exactly with no overlaps. Okay, so those are the pictures that I want to show you right now. Now let's. So far, all the fundamental domains we've discussed are parallelepipeds, but I said in the beginning that they could be general measurable sets, and they could be. They don't have to be connected. Just to give a stupid example. So example, if we take this example, will be relevant to the proof that I'm about to give of a statement. So if we take the lattice being Z2, I'm going to draw you another picture of a fundamental domain. So I can take the standard square, which is a fundamental domain, and divide it up into 2 pieces. Maybe this would be a triangle. Let's call it A1. And here are some more lattice points. So lattice point here, there's a lattice point here, there's a lattice point here, there's a lattice point here. And I can talk about A2. And okay, you have to be careful, of course, with the edges of these pieces, whether these sets are closed or open or contain their boundaries. But A1 union A2 is a fundamental domain.
And Barak, can you show that all fundamental domains have the same Lebesgue measure?
Exactly. That's my next. That's exactly the next proposition. So you're seeing in this. Picture that. Oops, what am I doing? Yeah, you're seeing in this picture that these 2 pieces, when you take A1, take A2, and you can translate it over here, you can get translated by an integer vector, by the vector 2, 0. Then these 2 pieces fit together to form the original fundamental domain. So in particular, they also have the same, the union of these 2 pieces has the same volume as the fundamental square, and that's not an accident, exactly as Shai is saying. And that also shows that this is a fundamental domain, right? If I can take any element in Rn, find a representative in the square, either the representative is inside A1, and if it's not in A1, if it's over here, then I can push it further by another element, exactly the element taking this square to this triangle, and find a closer representative in A2. And so that's why this is a fundamental domain. Okay, let's write down the proposition that Shai is asking about. So if A and B are 2 fundamental domains for the same lattice, then they have the same value. So I'm just going to define a map between them. So for each B and B, define L and L. So I'm defining an element of L, which I'm denoting by L of B, and I'm defining an element of A, which I'm also denoting by A of B, by the requirement A equals B minus L. So by property 2 of a fundamental domain, this is well defined. There's a unique, you can do this for every A, and you can do it in a unique way. So we're really defining a map from B to the set A and to the lattice L. In fact, we're defining two maps. And let's also define a subset of B for any fixed L0 and L. We're going to define a subset BL0 is the set of B and B such that L of B is L0. Okay, I claim that this is a measurable subset. So BL0 is measurable. In other words, it's a Borel set. Why is BL0 a Borel set? This is because BL0 is nothing but the intersection of B with A plus L0. The intersection of two measurable sets, right? This formula here says exactly that B, well, first of all, B is an element of B, but also it can be written as A plus L for some element of A. So that means that it belongs to this set, and by the uniqueness, it's exactly equal to that set. So this is why BL0 is measurable. And the uniqueness property means that by the uniqueness in part 2 of the definition, we can write B as the disjoint union of the BLs and A as the disjoint union of BL minus L. So we've decomposed B and A into countably many pieces, which are measurable and differ from each other by translation, and therefore the volume of B is the sum of the volumes of the BLs, which is the sum of the volumes of BL minus L, which is the volume of it. So that proves the proposition. Okay, so in general, there could be many fundamental domains, and you're free to choose your favorite fundamental domain depending on your applications. Let me stop for a second because I see some stuff in the chat. So can everybody hear me now? I can't hear anybody, so I don't know if that's good or bad.
I can hear.
Yes.
Okay, good.
I think
So
almost everyone.
this is sorry, Shai, what did you say?
Just that almost everyone can. Tomer couldn't,
Almost.
but now he can.
Okay.
Yeah, I have some problem there. You don't have to.
Okay. So sometimes you want your fundamental domain to have better properties than just to be a general measurable set. And in fact, often when people in the literature talk about a fundamental domain, they actually mean a nicer kind of a set. And that's, I'm going to call that a fundamental polytope, the definition. A fundamental polytope minus L. There's a set K in Rn, which is the convex hull of a finite set. So that means there's some P points. P doesn't have to be equal to N. It could be larger, but we won't say what it is. It's just a finite set. And K is all convex combinations of elements of this finite set. This is what it means for K to be the convex. So this is what it means for a set to be a polytope. And what I mean by being a fundamental polytope for L is that Rn is covered by the translates of L by K, and the interiors of the sets L plus K for L and L are disjoint. Okay, so in the previous discussion of a fundamental domain, we wanted this union to actually be a disjoint union, so an honest partition. And now we're making the set K nicer in that it's the convex hull of a finite collection of sets. And the price we're paying is it's no longer true that this is a partition. Points could overlap, sets could overlap, but they overlap only along the boundary. And these sets are nice, they're polytopes. You'll see that, in general, there's no reason, it's just not true. Yeah, let me just leave it to you to think about. Why is it impossible to find set K for which this is a disjoint union? Set K, which is a polytope, for which this is a disjoint union. I'll leave that to you to think about. There are many arguments, but they all involve topology in some way or another. And if we want to cover things exactly uniquely, we have to sacrifice something in how nice the set is. But we might be happier covering almost uniquely with overlaps only along the boundary. Okay, more picture. Well, okay, now let me define the Voronoi cell. The most famous example of fundamental polytope is the Voronoi cell. Okay, let's see. So, examples. First, we had the examples from before. So 0, 1 to the n is a fundamental polytope for C to the n. And notice that I've stuck in the right-hand boundary, so now things are no longer disjoint, but now this is a polytope. And A applied to this is a fundamental polytope for AZN. So if we take the previous fundamental parallelepiped and add the boundary, we get a fundamental polytope. Another example, which is very important, is the Voronoi cell. So it's defined as follows. So K is the collection of X and Rn such that for all L and L, the norm of X is less than or equal to the norm of X minus X. So points at least as close to 0 as to any other point of it. So this is we're using the Euclidean norm here. So maybe I'll write that down. This is the LT norm. in Rn. And what this formula is saying is this is the distance to 0. This is the distance to some other lattice point. And so this means that x is closer to 0 than it is to the lattice point. There might be a time. Okay, but it's definitely not further away from 0 than from L. So if every point in Rn has a closest neighbor in the lattice, could be more than one. If that closest neighbor is the origin, or more generally, if the origin is one of those closest neighbors, then you belong to the Voronoi cell. And so you're going to see some exercises. The exercise sheet should appear on the page this evening, and you're going to already see some exercises. And so exercise number 1 is the Voronoi cell is a polytope. So it's a convex object which is the convex sum of a finite number of points. Let's just draw a picture. So this is like a hint and a proof of the convexity. It's not a proof that it's the convex sum of a finite number of points, but at least a proof that the Voronoi cell is convex. Notation. Voronoi, the Voronoi cell. Okay. Here's a hint. So the Voronoi cell is the intersection over all L in L, X in Rn, such that okay, so why is this? This is just a definition. I'm just pulling this quantifier out of the brackets, and so I'm getting this description. And so let's think of each one of these pieces individually. This thing you can talk about. This is closure of one of the connected components of Rn minus Rn such that x equals x minus c. You can take the condition of equality in this formula, and that defines a set. That's this set over here. And this set is actually an affine plane, an affine hyperplane of dimension n minus 1. So this is an affine hyperplane. And the affine hyperplane subdivides space into two connected components. One of them is a set of all points which are closer to 0 than they are to L, and the other is a set of all points that are closer to L than they are to 0. And we're choosing one of those two connected components. So this thing is the intersection of a countable collection of convex sets, and it's a trivial exercise to check that an intersection of convex sets is convex. Okay, so this proves the convexity, and so the picture. I'm not just proving convexity, but I'm also sort of giving you a way to think about the Voronoi cell. If this is the origin, and here are some points of my lattice. L, okay, then basically what I'm doing is for every non-zero element of L, I'm defining a plane, a hyperplane. Let's make this hyperplane here. Okay, everything on this side of the red line is closer to 0 than it is to U2. And everything on something like this, everything on the left side of the blue line is closer to 0 than it is to U1. And if I do this for all elements of the lattice, eventually what I will get is a non-empty convex set, and it's going to be bounded by boundaries that look like this, and eventually that's going to be the Voronoi cell. Okay, so that's sort of the geometry of what's going on. Let me show you some pictures of Voronoi cells. So this is the Voronoi cell picture. Let me just remind you, the Voronoi polytopes, if you take their translates, they cover space without overlaps, except overlaps at the boundary. So in particular, they're giving you a kind of a periodic tiling of Rn. Okay, this is called tessellation. And so the tessellation associated with the lattice that we saw before, the hexagonal lattice that we saw before, is this hexagons, and that's why this is called the honeycomb lattice or the hexagon lattice. Actually, this lattice is, I took my lattice to be the origin, and then E1. I mean, what I call the hexagonal lattice is this lattice rotated by by 30 degrees. Okay, because I took, this is a point in the lattice. What I'm saying, correct? No, I'm sorry. That's erase my comments. Let's kill the recording. This is the origin. This is E1. This is the other generator of the honeycomb lattice. These blue points, and the set of points closer to this point than to all other points is this hexagon, and this hexagon is the Voronoi cell in a tile space. Okay, here's some pictures in 3 dimensions. These are some possible pictures that you might see for Voronoi polytopes in 3 dimensions. We have the cube that we already saw for Zn, and we have these objects. Now, if you think about this a little bit, you'll see that these polytopes, first of all, they're all different geometrically, but most of them are different from each other combinatorially, which means they might have a different number of points on the boundary, or their faces might be different. So for example, this guy is different from this guy because this guy only has quadrilaterals as faces, but this guy has a hexagon as one of the faces. This guy and this guy are also combinatorially different because here quadrilaterals touch quadrilaterals, but here each quadrilateral does not touch other quadrilaterals, and so on. So you can think of these Voronoi polytopes and think about their combinatorial pattern. And there's a lot of questions about these combinatorial patterns, and the number of these combinatorial patterns as the dimension increases and all the possibilities. And so you're seeing 5 different Voronoi polytopes, and only 2 of them are combinatorially the same, these 2, but they're geometrically different.
Is every polytope that can tile a space a fundamental polytope of some lattice?
No. I mean, you can take, a fundamental polytope. You're not asking if it's a Voronoi cell. It's every lattice, every polytope tile space. No, it might not. Okay. Let me think for a moment. Right.
Up to volume, maybe? Like you can always multiply by a scalar and then it's not fundamental, right?
No, the co-volume of a lattice can be anything, and the volume of the fundamental polytope is equal to the co-volume. So the volume doesn't really give you a restriction. Okay, there's a bunch of questions about which about whether, okay, the short answer is I don't know the answer, and the longer answer is we'll get to some similar questions later in the course, and when we do, by that time I might know a little bit more about the answer to your question.
But Bach, what about
general,
the cube of side length pi? That can't be a fundamental.
It tiles. No, it tiles. It's a fundamental polytope for the lattice pi times Dn. We're allowed to dilate lattices by LNR.
What can you?
Lattices don't have covolume 1.
Can you repeat?
The question was, does every poly? Yeah, let me write it down because it's an interesting question. And
Because
there's a lot
then
of
if you look
research
at the
around
plane
relevant
and you look at the polygon with many you might
Well, let me
construct
write down
something
the
which is
question as I
not a
understand it.
lattice but a discrete group somehow. No, can't you come up with a very
Let me write down
acute
the question.
triangle?
Wait a minute. Let me write down the question. So all polytoids, is it true? So, is it true that any polytoid that tiles Rn is a fundamental polytoid? For sunrise. Okay. Now,
Barak, if
I'm
you
not going to
take
ask.
pi the cube, then it's not. It doesn't generate a lattice because
Oh,
it's
exactly.
irrational. So you wouldn't get a lattice.
No, okay. So if you take, okay, I'll make the question better understood. So if you take this is the polytope that you're discussing, right? Shine. This is a fundamental
Sorry.
polytope. For the lattice pi zn. In other words, the matrix, diagonal matrix with pi on the diagonal is pi to zn. Okay. Let me say a few words about the question, and then we'll go back to the person who asked the question. So you could ask yourself, what does it mean? What does this word that tiles means? It means, I guess it should mean that you're tiling space by a translate of the polytope. You can translate the polytope around and tile space. Is it true that whenever you can do that, you can also translate it around by elements of a lattice, in other words, in a periodic fashion, in tile space? Now, if you're also allowed to rotate, if you don't only insist on tiling by translations, but tiling by isometries, then the answer is false. The simplex, the symmetric simplex tiles space. I'm sorry, the symmetric simplex, at least in 2 dimensions, the symmetric simplex tiles space, but it's not a fundamental polytope for a lattice. Okay. In higher dimensions, it's not clear in which dimensions simplices tile space, but some objects definitely tile space if you allow rotations and they're not like half of a cube will tile space, and it won't be a fundamental polytope. But tiling by translation, I'm not really sure about the answer to this question. Are there any? Was that the question that was asked? I'm not sure.
Yeah, it was.
Sure. Okay.
Thank you.
So I don't know the answer. We'll leave that open, and maybe we'll have time to discuss it further down the road. Let me say one more thing about fundamental domains, fundamental polytopes, and then we'll take a break. So this is about sublattices. So proposition, this is really important. Proposition. Suppose you have an inclusion of lattices. So you have 2 lattices, L1 and L2. Omega 2 is a fundamental domain for the lattice L2, sorry. And the set xi, I is in some indexing set, let's call it curly I, are coset representatives. For the quotient group L2 over 1. Then omega 1, which I define to be the disjoint union of omega 2 plus xi and I. This is a fundamental domain for L1. And the cardinality of I, which we can denote by D, is the index of L2, L1 and L2. So far, I haven't said anything, but there's a formula for it. It's the quotient of the covolumes. And therefore, it's a finite number.
Can you repeat
Okay,
the claim?
so let me make this a little bit smaller so we can see the statement again. So you have, was there a question?
Yeah, it was just like I just wanted to see like the whole thing.
Okay.
Thank you.
So we have an inclusion of lattices, L1 and L2. So in other words, L1 is denser than L2. Sorry, L2 is denser than L1. L1 contains some of the point of L2, but not all of them. But both of these guys are lattices. Omega 2 is a fundamental domain for L2. At this point, when I start the statement, I only choose coset representatives, and I'm not claiming that they're finitely many. At the end of the discussion, I am claiming that the cardinality of the coset space is finite. It's finite because it's a quotient of two real positive real numbers. And because these numbers are the determinants of some matrices, absolute values of determinants of some matrices. It's also an integer because now it's a finite number, which is an index of one group over another. This is the group theoretic notation of an index of one subgroup inside of another subgroup. And along the way, what you see is you construct an explicit fundamental domain for the lattice L1 in terms of the fundamental domain for L2 and these coset representatives. So that's the statement. Proof. By the fact that the xi's are coset representatives, we find that any element of L2 can be written as an element of L1 plus one of the coset representatives. Okay. Now let's look at omega 1. Omega 1 is defined over here. So clearly omega 1 is Borel set. And also clearly it's disjoint, because if two of these guys intersected, that would mean that we'd have 2 points which are equivalent by how to say, okay. Let me just leave that to you. So I'll just write that down. So clearly omega 1 is a Borel set because it's a union, it's accountable as most union of Borel sets. And the so this is, I'll leave that to you as a small exercise using that. The xi's are coset representatives, and omega 2 is a fundamental domain. So the uniqueness in the definition of coset representatives and in the definition of the fact that omega 2 is a fundamental domain gives you that this union here is a disjoint union. I need to clarify, put these brackets around this. Okay. And so what that means is then that the covolume of L1 is the volume of omega 1. That's a formula that we already proved. This is D times the volume of omega 2, which is the volume, which is D times the covolume of L2. And in this formula, you see that D has to be a finite number. So, and you get our formula. Okay, so divide by the volume of L2 to get this formula. So, and let me write down a corollary, which we're going to use after the break. Corollary, if you have an inclusion of lattices, and D is the index, then L1 is contained in L2, and L2 is contained in D times L1. Okay, right? That's just a general fact from group theory. If you have a finite index subgroup and you take elements of a small group and multiply them by the index to themselves, D times D divides, D is divisible by the order of each element in the quotient. And so what that means is that L2 is contained in D times L1. Okay, let's take 10 minutes. So let's meet at 12:16 and continue after that.
Professor, can you zoom out a bit and return to like the proposition itself? Thank you.
The statement here, like that?
ברק, מהמשפט פדורוב הזה, אם לוקחים את הפוליטופ, כאילו פוליטופ נגיד שהוא אומר שלא יכול להיות פונדמנטל נגיד בדו-ממד, ואז עושים לו כמו עם קטע או עם מרובע, כאילו בממדים שנשארו זה לא כאילו כבר אומר שיש בכל ממד דוגמה נגדית.
לא, רגע, בממד 2 אפילו עוד אין לנו דוגמה נגדית, נכון? את צריכה, כל מה שפדורוב אומר לך זה שאם את מסתכלת על תאי וורונוי בעצם, על פוליטופים כמורים שמרצפים, אז הם צריכים להיות או משושים או מקביליות, אלה גם תאי וורונוי. אלה בדיוק ככה נראים בדיוק תאי וורונוי. למעשה המקבילונים, נכון, אתה צודק, המקבילונים הם, דוגמה נגדית לשאלה, נכון, המקבילונים, יש מקבילונים שהם לא תאי וורונוי, והם כן מרצפים.
אבל השאלה לא הייתה על וורונוי, נכון?
סליחה, לא שמעתי.
השאלה לא הייתה על וורונוי, היא הייתה על המקביל היסודי, המקבילון היסודי, כמו שלא קראת.
נכון.
פוליטופים יסודיים.
נכון. אז אין פה, בממד 2 אין כאן דוגמה נגדית, ולא ברור, לי לפחות לא ברור מה קורה בממדים יותר. אני חושב שמה שאת אומרת הוא הגיוני, אבל זה גם לא טריוויאלי, שאם יש לך דוגמה נגדית בממד מסוים, אז את יכולה כאילו לשדרג את זה לדוגמה נגדית בממד יותר גבוה, אבל זה גם לא לגמרי מובן מאליו. צריך מאוד להיזהר, יש פה הרבה שאלות שהן תמימות בפוליטופים על ריצופים, והן קשות מאוד, אז אני לא בדיוק יודע את ה...
כן, זה מגניב. אז אתה אומר שגם בעצם בדו-ממד, זה לא אומר שאין, שמצאנו דוגמה שהיא...
לא, אני חושב שבדו-ממד אפשר לחשוב שהתשובה היא כן, נכון? בדו-ממד אנחנו מקבלים שכל האובייקטים שהם מרצפים, סליחה, כל האובייקטים שהם תחומים יסודיים לסריגים, הם או מקבילונים או משושים, ואני חושב שזה גם ידוע שאלה
ריצופים אסימטריים, כן.
כן, הסימטריה אולי בעתיד, אולי אפשר לרצף, האם אפשר לרצף בהזזות על ידי גוף כמור שהוא לא סימטרי.
כשאתה אומר סימטרי, הכוונה היא כאילו, שיש ציר סימטרי כלשהו, או
שהוא לא סימטרי לשיקוף במרכז שלו. לא שיקוף.
זה שיקוף כלשהו.
לא, ש-X, אם קורדינטה, אז מינוס כל הקורדינטות.
כן, אם אנחנו מזיזים אותו כך שהמרכז הכובד שלו, מרכז המסה שלו באפס, אז סנטרלי סימטרי זה אומר שעם X בפנים, אז גם מינוס X בפנים.
אוקיי.
אז...
אני די בטוח שמשולש משוכלל ולא סימטרי מרכזית, כן? ואפשר... אבל לא, אי אפשר לרצף רק על ידי הזזה, כאילו.
משולשים לא מרצים על ידי הזזה. יכול להיות שיש משושים או מרובעים שכן מרצים על ידי הזזה והם לא...
רגע, אנחנו מבקשים ריצוף רק על ידי הזזה או גם על ידי סיבוב?
כן, אם אנחנו מאפשרים סיבובים, אז הטענה היא לא נכונה בדיוק באמצעות משולשים או בממדים יותר גבוהים סימפלקסים, בממדים מסוימים. אבל כן, אני חושב שיש מעין... זה הכל ציור, צריך להסתכל על ציורים של אשר, אז אני חושב שיש מין מרובע כזה, כן, הנה דוגמה, אם אני אקח, לא ברור לי בעצם.
אם אתה יכול לרצף על ידי הזזה, אז הצלעות חייבות להגיע בזוגות מקבילות, כן? והמצלה כמובן.
בשני ממדים.
בדומה, כן. בתלת ממד הן צריכות לבוא בפאות בזוגות, כן.
בגלל זאת אומרת, לכל פאה צריכה להיות איזושהי פאה שמקבילה לה, אבל כן, ולכן הן באות בזוגות של פאות מקבילות, אתה צודק. אז אולי נעבור למשושי.
אני חושב שלפחות משושה זה כבר אומר שהוא סימטרי מרכזית.
לא אמרתי שהוא משוכלל.
כן, אני יודע. משושה עם צלעות מקבילות.
האם אנחנו יודעים שזה למשל לא מרצף? טוב, בואו, הדוגמאות האלה נותנות את התחושה שהתשובה היא שאולי כן, אבל אני לא רוצה כרגע לחוות דעה.
יהיה על מה לחשוב.
כן. יש לי עוד דברים לחשוב עליהם, אבל אני אחשוב על זה. Okay. All right, so we can continue. So the next topic is still algebraic, and this is about, you saw a little bit of it at the end of the last lecture, and this is about sublattices and how do sublattices of lattices behave, and what about subgroups of lattices? So sublattices and subgroups. And there's a technical theorem, which I'll spend a little bit of time proving, which gives us a structural result for a sublattice inside a lattice. So it's somewhat technical, so I'll write it down first and then we'll discuss it. So theorem. We have two lattices in Rn, and there's an inclusion. So L1 is contained in L2, and they're both lattices in Rn. And there are two statements with some kind of a symmetry. So given a basis of L2, there's a basis of L1 such that, and I'm going to write down the basis ui in terms of the basis vi and a certain triangular integer transformation. So u1 is a multiple of v1 by an integer that I'm calling m11. u2 is integer combination of v1 and v2, all the way down to un. Okay, where I have these numbers m, I, j are integers. They're indexed such that I is the bigger index, and they range from 1 to n, and mii is never 0. Okay, so this formula we're going to call, this formula with these restrictions on the coefficients in the formula, we're going to call star. And so again, the quantifiers are, we're given a basis of the bigger lattice, and we can find a basis for the smaller lattice, which is somehow adapted to it, can be obtained from it by certain integer, certain operations over the integer. So it's some kind of a reduction theorem or a way of choosing a preferred basis for the sublattice given a preferred basis for the big lattice. And the second statement is a similar statement, but we reverse the roles of the sublattice and the lattice. So given a basis u1 up to un of L2, there's a basis v1 up to vn of L1 such that star holds for some choice of v on mj. Okay? So you'll see the proof is some kind of long induction, and it's not terribly deep, but it's not immediate, and it's very, very useful. So let's start with the proof of A.
Did you confuse the roles of L2 and L1 in the second statement? You want to start with the basis of the smaller lattice and reconstruct
Oh,
it?
yes, thank you,
Okay.
thank you very much. Well, there's a kind of a universal rule in mathematics that whenever you choose symbols for different things, you try to choose them so that they look exactly the same to maximize confusion, right? So somehow the U's always will get matched up with the V's in every situation, particularly for when the handwriting doesn't distinguish them, the I's get confused with the J's. And so I'm sort of respecting a long-held tradition here. But the U's should correspond to the L1s and the V's should be in L2. That's because in the alphabet, U comes before V and 1 comes before 2. So there's supposed to be some kind of a logic to the notation. Proof. So let's let D be the index of L2 and L1. And so for every V in L2, dV belongs to L1. Again, D is the order, is the cardinality of this coset space, which happens to be a group. And we can think about V and project it to the quotient group. And then it's an element of a finite group. Then it has an order. The order divides the size of the group. So that gives you that D times V is the trivial element in the quotient group, which means exactly this. Okay? So that means that we can find so what I can do, I can start with I can make the following definitions. So UI equals dvi. If I take the UI equal to dvi, and if I take mii to be d and mij to be 0 for I not equal to j, then I put myself in exactly this kind of a situation. The mii are non-zero, all the mijs are integers, and actually it looks like just a diagonal thing. All the off-diagonal terms are 0, and the ui's are in L1, but I want the ui's to be a basis of L1, and I haven't guaranteed that. Okay, so I have found some way of solving this with elements of L1, but they might not be, they might not form a basis. Okay, so now I'm going to, of all possible ways of fulfilling star, so now there's one way at least to fulfill star, and of all the possible ways for fulfilling star, I'm going to choose one way in which M11 is minimal. Okay, let me write that down. So now choose a solution of star. Solution means I want to solve both for the UIs and for the coefficients Mij, such that M11 is as small as possible. And on top of that, inductively, if u1 up to u minus 1 have been chosen, then I take MII minimal, as small as possible again. Okay, so let's explain this. Let's go back to star. I know that this formula can be solved at least in one way with certain UIs in L1 and certain MIJs, and I first choose that collection which makes M11 as small as possible, and then define U1 to be this thick. Okay, there may be more than one way to do that. I just choose one of them. Now U1 has been chosen, and now I continue and I choose U2 so that this guy no, I'm confusing. Yeah, now there's at least one choice of containing U1 of U2 up to UN for which this can be solved, but there may be many. So I choose that choice, making this coefficient as small as possible. And then I continue like this, and I find some choice with this complicated minimality property. And now we want to show, with these choices we claim, that U1 up to UN is a basis of L1. So if that's false, then L1 is not equal to the, or let's write it this way, then the span over Z of the UIs is a proper subset of L1. Right? Each one of the UIs belongs to L1 by construction. And so certainly we have an inclusion. If we had equality, we would be done. So the case that we care about is the case when this inclusion is a proper inclusion and there's an element which doesn't belong to, which belongs to L1, but doesn't belong to this Z span. So let's take that element and call it C. So let C be an element in L1 and not in this Z span. And we can write C as an integer linear combination of the VIs. And that's because C is in L1, right? C is in L1. L1 is contained in L2, so C is also in L2, and the VIs are a basis for L2. So we can write C in terms of the VIs. So C is an integer linear combination of the VIs. And let's define K to be the last index in this way of writing things, which is non-zero. Okay? And in addition, choose C so we can do this for every C which is in this in the complement of this Z span inside L1. We can do this, and K depends on C. Of course, every element C has a unique expression in this way because the VIs are a basis for Rn. So there's a unique way of doing this, and we just choose it so that tk is the last non-zero digit, last non-zero integer, and then we choose c so that k is as small as possible. So let's look at mkk. mkk is not zero. Mkk is the coefficient. We've already chosen our ui's, what it started on. So mkk is the kth diagonal coefficient in this formula star, and it's some non-zero integer. And we can divide tk by mkk, possibly with remainder, and we find an integer s such that tk minus s and kk is smaller in absolute value than mkk. Right? Whenever you have two integers and one of them is non-zero, you can always subtract off multiples of one integer from another so that the remainder is smaller in absolute value. It could be zero, but in any case, it's smaller in absolute value than mkk. And now let's look at the vector c minus suk. C minus suk, t1 minus s and k1, v1 plus plus tk minus s and kk. Okay, and this vector here belongs to L2, and actually, sorry, belongs to L1. Right, because C belongs to L1 and UK belongs to L1. So this is an element of L1, and we chose K minimal so sorry, it belongs to L1 if C minus SUK is in the Z span of the UIs. Take this away. If C minus SUK were inside this span, then we would also have that C was inside of this span. Right? Because we subtracted an integer multiple of UK, and that keeps us inside this span. So this is impossible. Oops, contradiction. We chose C outside of this span. So then we get that C minus SUK is also an element of L1 minus the Z span. Okay. Since K was chosen minimal in the definition of C, this cannot be zero. So we can't have TK minus S and K equals zero. But this contradicts the minimality in the choice of MKK. When we chose MKK, we were choosing it minimal with respect to the property that we could find elements in the in L1, which for which we can solve this formula here. And now we're showing that we can solve it with a smaller value of MKT. So this is a contradiction, and this proves part A of the theorem. Fortunately, B is not harder than it follows from A. You could also prove it directly, but then you'd have, again, a complicated induction. But actually, you can sort of apply the work we already did. So let's let U1 up to U1 be basis. One, and D is the index as before. And now we already saw that we have an inclusion D times L2 as contained in L1, so we can apply what we did in part A with the inclusion L1, L2 replaced with the inclusion DL2 contained in L1. So in other words, now this lattice is playing the role of L1, and this lattice is playing the role of L2. And so what we get a basis, which I'm going to denote by dV1 up to dVn of dL2. So that, let's call this the double star now. dV1 is W11 V1, dV2 is W21 U1 plus W22 V2, etc. dVn Wn1 U1 plus Wn Un. These Wij's are integers, the Wii's are not zero. And now you can solve double star for Ui one row at a time, sequentially. So you know that solving a linear equation is linear algebra. Solving a linear equation where it's already in triangular form is much, much easier. So we just solve the first equation, and we get that we move the W11 over to the other side. So we get that U1 is, let's call this M11 V1, where M11 is 1 over W11. So this is now a rational number. We don't know that it's an integer at this point. And U2 is M21 V1 plus M22 V2, and so on. Now, we've written the UIs as in terms of the VIs as combinations, but the UIs are living in, let's look at this for a moment. The UIs live in L1, which is a subset of L2. And so there's a unique way of writing the UIs as linear combinations of elements of L2. And in that unique way, the coefficients become integers. So since there's a unique way of writing X and Rn as a linear combination of the elements V1 up to Vn, and since the Ui belong to L1, which is contained in L2, which is the span over Z of the Vi, the Mij have to be integers. And that's all, that proves part B. Okay, so this was a bit of a technical statement, and now let's draw some corollaries of this. So one thing that I'm going to go back to the statement for a while and explain why we care about this statement. So there are many things what one can do with this statement. The first thing that you can do with this statement is you might want to, given an index D, you might want to describe all sublattices. So suppose L2 is fixed and D is fixed. D is the index of L1 and L2. And question, is there an algorithm for specifying the all possible sublattices of a given index? Is there a easy computation of the number of these sublattices? You can get that from this statement, and that's going to come about using a theorem. So this will be corollary 1. In the theorem, can arrange that MII is positive and MIJs are all non-negative and bounded above by MJJ. So let's call this property property 1, and let's call this property property 2. So MIJ is between 0 and MJJ. Okay, so I'm claiming that you can get certain bounds on the sizes of these coefficients. In particular, what you're seeing is that this is a finite number. And if you think about it for a moment, you can see that if you take different numbers in this range, different coefficients in this range, you're actually going to come up with different sublattices. So this is really is going to give you a one-to-one correspondence between a given lattice with a given basis and certain sublattices with their own bases. And so here's the proof. If you want MII to be positive, all you have to do is replace UI by minus UI. Well, suppose if it's sorry. Let me write this more. To obtain 1, if so MII is some non-zero integer. So if it's positive, do nothing. And if it's negative, replace UI with minus UI. Okay. And so now to obtain this case 2A, now we're in case A, and we are going to replace the UIs with UI primes, which are written in the following way: TI1 UI plus etc. plus TII minus 1 UI minus 1 plus UI, where TIs, the coefficients, are obtained as follows.
Is the first one maybe supposed to be TI1 U1 and not UI?
Yes, thank you.
Okay.
So I want to give you an algorithm for figuring out what TIs you should use here so that the UI primes will have the property that we want. And so here's what we do. So notice that for any choice of these TIs, the UI primes are a basis of L1, right? The UIs that we got from the theorem, they're a basis of L1. The UI primes are obtained from the UIs by some kind of linear combinations. And so definitely the Z-span of the UI primes is contained in the Z-span, is contained in the Z-span of the UIs. Definitely each UI prime is inside the Z-span of the UIs. But the coefficient in front of UI is 1. So you can also inductively solve for UI in terms of the UI prime. You can sort of invert this system of linear equations. And then you get that each UI is also in the Z-span of the UI primes. So no matter how we choose the TIJs, if we work with this kind of a formula, which is kind of a triangular formula with ones on the diagonal, then it's invertible over integers. And that's going to give us that the Z-span of the UI primes is equal to the Z-span of the UIs. We know from the theory that the UIs are a basis of L1, so the UI primes are also a basis of L1. And so far I haven't showed you how to choose the TIs. I'm just telling you that we're getting a basis. But now we can think about what happens to the coefficients of the UI primes in the formula star. So UI prime also satisfy star with coefficients that I'm going to call Mij prime, which are computed as follows. N prime II equals MII, and N prime IJ equals TIJ NIJ, sorry, MJJ. Okay, so what I'm saying here is that the UIs satisfy equation star with some coefficients. And now I've given you a definition of UI prime, which depends on some coefficients Tij, which I haven't told you yet. But I'm saying that no matter which coefficients you choose, the UI primes will also satisfy star with some new coefficients, and these are the new coefficients. Okay, so this is, oops, these are the new coefficients. So this is something that just follows from this formula. You just check how to express the UI primes in terms of the VIs, and you see that the coefficients look like that. So now how do we choose the TIs? So for each I, successively, again, we do this starting with for each I, we do this successfully starting with Ti, comma I minus 1. So choose Ti, I minus 1, and then choose Ti, I minus 2, etc., guaranteeing that each step that this holds. So if you look at this formula, you can always use the last coefficient to reduce Mij prime so that it's less than Mjj. Okay, I'll leave that as an exercise for you to check the details. It's technical, but it's not very deep. I'm also going to plug in cable. So I'll leave that as an exercise, so check. And the case of 2b is also an exercise. So this is a proof of the first corollary. Let me write down, we have about 10 more minutes, so let me write down some corollaries. And I'm not sure, I want to state them all, and I'm not sure I'll have time to prove them all. So let me first state them. So second corollary, suppose we start with elements of a lattice L, which are linearly independent. Okay, I'm not saying there are n of them. There are some k less than or equal to n vectors, which are linearly independent elements of a lattice L. Then I claim that there's a basis V1 up to Vn. Well, we can do the same thing with subgroups, which are subcollections of k elements, which are not necessarily of full rank. So then there's a basis V1 of Vn up to of L, such that I can solve same equations as before, but only up to k. Okay. And so these guys satisfy the same equations. As in the first corollary. For k's between, for I and j's between 1 and k. Okay, so this is immediate, so let me just write down the proof of this proof. So choose UK plus 1 dot 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 UN in L such that U1 UK plus 1 UN are linearly independent, and apply corollary 2 with L1 being the span of the UIs and L2 is L. So that's exactly what you get, because star, I mean, you see that the restrictions that we have on the coefficients are exactly the restrictions that we had in corollary 2, and UK plus 1, we don't care about UK plus 1 up to UN, how they're, this system of equations is just a subcollection of the system of equations guaranteed by the previous corollary. So that proves corollary 2. Now corollary 3. So suppose I take k linearly independent vectors in a lattice L, then the following are equivalent. First one is I can complete these UKs to a basis of L. So there are, I want to know when given in a k tuple of linearly independent vectors in a lattice, I want to know whether I can complete them to a basis. So that's the first item in the equivalence. And the second equivalence is the span over R of U1 up to UK is the intersection of L with the span over Z of U1 up to UK. So this corollary is quite important. I think I'll have time to show you the proof, but I'm not exactly sure. Let me, again, explain what we're talking about and why we care. So you're given, you want to basically, in some cases, you'd like to find a basis for a lattice, and you might want to do it inductively, and you choose k vectors, and you want to know whether you're on the right track. In other words, you want to know whether you can continue and add vectors to this collection to end up with a basis of L. And that's what item 1 says. And item 2 says that happens if and only if you look at the space spanned by the vectors you've chosen over Z.
Professor, I think you got it wrong there. You mixed the R and the Z.
Oh,
maybe.
sorry. Thank you very much. This should be an R, and it should be a Z. Yeah. So if you want to know, thank you. So you want to know whether you can do that, you look at the Z span of these vectors, and that should be exactly the same as the R span intersected the lattice. Okay? So there's an obvious inclusion here. If you have an element which is an integer linear combinations of the UKs, certainly it's an L because these elements are in L, and certainly it's also a real linear combination of UI, so it's here. So the inclusion, I don't know if you can see this, but the inclusion of the left-hand side is contained in the right-hand side is immediate. And the content of this is the converse inclusion. And that does not always hold, but it holds if and only if you can complete these elements to a basis of the lattice. And let me, so I'm not going to have time to prove it to you today, so I'll make a decision on whether to give you the proof next week or to distribute the proof. But let me write down a special case of this, which is important. So corollary 4, sorry. So a vector U and L can be completed to a basis if and only if I have A, U in L, a real number implies A is an integer number. So all the elements of, in other words, the line span of U intersects L exactly along multiples of U. So let's draw a little pic. Well, I don't have time for a picture, but let me just give a definition. So definition, if this holds, if the property of corollary 4 holds, U is called a primitive vector of L. If the property of corollary 3 holds for U1 up to UK, the span over Z of U1 up to UK is called a primitive subgroup. Of L, and U1 up to UK is called a primitive k-tuple. Okay, so next week I'll be using this notion of primitive subgroups and giving you some examples, and probably I will, so corollary 4 is immediate from corollary 3, and I think I will just post the proof of corollary 3. It's some kind of similar algebra, posted on the course webpage so we don't have to go into it next week. Okay, so are there any questions, or are there any questions? We can go over time and answer questions. And if
Can you
not,
quickly go to the end of your notes? Just
sure.
Okay.
Okay, so thank you all for coming, and I'll see you next week.